Okay, I just sent you all an email, so you may not have gotten it yet, but I have to be out of the office today from 9 to 10. Or thereabouts, because I've got a calculus challenge meeting, so if that's an inconvenience for anybody, just let me know after class. So we were walking down the road, trying to prove this fundamental theorem of Galois theory. And so I gave you this lemma and the one after it last time. So I'm going to repeat this lemma. I'm going to go through the proof of it. I'll repeat the next one, and I will let you all do the proof of that because it's very similar. So you have L inside of M are intermediate fields to the extension K inside F. If the degree of M over L is finite, then so is the index of M prime and L prime as a group. And in fact, the index is less than or equal to the degree of the field extension. In particular, if the degree of F over K is finite, then your Galois group of F over K is less than or equal to the degree of distance. And I probably won't prove this last statement as it's an immediate consequence of what's above. So, proof. So, I'm going to notationally, I am going to let the degree of M over L be N. And what I'm going to do here is I'm going to proceed by induction on the and what we're going to do is well, if n equals 1, the result is and in fact, you get equality in the case of 1, because what happens is, what does the degree of M over L being 1 mean? It means that these two are the same field extension, and therefore, well, M prime, the index of M prime and M prime is also 1, right? So that's easy peasy, lemon squeezy. And what I'm going to do, so now we're going to assume the result holds for all. So if holds for all let's now I'm going to make a simplifying reduction in this case, and not only will this make my proof here easier, but it will also give us some insights into kind of the interplay with polynomials later. So we'll get to some of that later today. So we now reduce to a simpler case as follows. So let us select a U in M minus L. Since so find some U that's in M but not in L, and we can do that because we're assuming that N is bigger than 1, so this is actually a proper extension. So there must be something in M in L. Now, since the degree of M over L is finite, what's one thing that's important that we know about finite extensions of fields? That's true, and there's something else. Maybe it's even in the title of this course.
It's algebraic.
It's an algebraic extension. So in particular, algebraic over L. And so in particular, U is algebraic. Right. So let F be minimal polynomial of U over L. Since U is algebraic, it has to have this minimal polynomial. And note that degree of f of x is bigger than 1. And the degree has to be bigger than 1 because U is in M, not in L. If the degree of the minimal polynomial is 1, that would mean U would have to be in L. Right? So we can assume that this f is got degree, it's bigger than a linear polynomial. Look at the intermediate extension. Notice that LU is the smallest extension that contains L and U. So it's bigger than L because U is not an L, and it's contained in N, right? Might even equal L. But I do know this much. If K is the degree of that polynomial f of x, and that extension is of degree k. And what's the degree of this? Well, of course, the degree of this times the degree of this should be degree of M over L, which we said is N. So this would have to be N over K, which of course would have to be an integer, but I'm just going to leave it in that form right now. And let me point out here, if K, the degree of this extension, is strictly less than N. So this statement means that LU is actually a proper intermediate extension. It contains L strictly, and if K is less than N, then it's strictly contained in N. And so this is also less than N. If this is the case, then then this index right here, which of course we can break down this way. Is less than or equal to and so we've got what we need. So we are done unless perhaps. So this is the big reduction that I said. Hence, we can proceed under the assumption that M is actually equal to L joined with U, because otherwise we're finished by our inductive hypothesis. So how do we tackle the case where M equals L U? So in this case, we can assume that M is just generated by that algebraic element U that's in M minus L. So in this case, what we're going to do to take care of this is I'm going to give a one-to-one map from the cosets of M prime and L prime into the set of distinct roots of F and L. So remember, what we're going for here, the brass ring, is we want to show this this inequality, right? And of course, this is finite, and this is, of course, in our case, is n. So what we want to do is find a one-to-one function from the set of left cosets of M prime and L prime to the set of roots of f of x. And let me remind you, it's the minimal polynomial of u in Lx. Notice that I noticed originally I said the degree of f of x equals k, but now we know that the degree of f of x can be chosen to be equal to the degree of m over L. So k and n are synonymous here. Then this will show that L prime m prime is less than or equal to the degree. Because if there's a one-to-one function from the cosets of M and L into the set of roots of f of x, well, we know that this set of roots is a set that's no more than n, right? And of course, this is a set of size n, so we'll get the desired inequality. Everybody okay with it? So here we go. Let's try to set this thing up. We'll call this something. So let's let how M prime be a let cover set. And I am going to define a function to so roots of and how's this going to work? Well, let me make an observation first. If let's say that sigma here, I kind of want to type this notation again. What does it mean for sigma to be an M prime? It is an element of the Galois group of F over K that fixes everything in M, right? That's what M prime means. It just fixes M. So it's in the Galois group of F over N. So fixes this. So suppose you have an element of M prime and you multiply it by tau. So a typical element of that coset will look like a tau sigma. If U is in M, then tau sigma of U is the same thing as tau U. Right? Because by definition, the sigma fixes everything in M. So sigma of U is just U. Right? So the upshot of this is that so every element of the coset tau and prime has same effect on any U in M. Right? Because if any element of tau U has the same effect as tau, they all. So basically, if you have any element of this left coset and you have any element of M, it all does the same thing to that element U, and what it does is the same thing that tau does. So you can just sort of ignore the M prime part, if you will. And this observation allows us to construct our desired map. So we're going to define, let me give these things names here. I'm going to call the left cosets S and the roots capital T. So F goes from S to T. And how's it going to work? Well, my input is going to be tau and prime, and my output is going to be tau U. So notice that my input is one of these cosets, so it's a tau sigma. And what I do is I take u root of f of x. In fact, it generates m over L. Notice my input is tau sigma, my output right, but my input is this, I'm sorry, my input is this coset tau n prime. My output is tau u, right? And remember, what does tau do? Tau is an element of well, it's an element of L. So this is a left coset of n prime and L prime. So tau is an element of L prime. And what it has to do is it takes a root of f of x, the irreducible polynomial for u, to another root, right? So this is well defined. So it's independent of coset representative chosen.
So
We showed that on the previous board. Yes,
are we just fixing u as one particular root?
that is correct. Right, that's right. So it's the u that I alluded to earlier, that we had the u in m minus L, and we came to the conclusion that we could assume that m is L joined with u. So yeah, that I probably should have used something other than u. The u over here on this board can refer to anything, and m, the u here I'm specifically referring to as the root of f of x. So that hopefully that clears it up a little bit. This function is well defined. We showed that it's independent of the coset representative chosen over there, and since u is a root of f of x, and tau is in L prime, so it means it fixes the coefficient of the root of coefficient of the polynomial of f, then tau u is a root of f of x. So this is well defined in both senses. It's independent coset choice, and it goes to the place that I want. These are all roots of f of x. So what I want to do here, so I'm going to totally vanquish this problem. I hope, if I can convince you all that this is actually a one-to-one function, right? So what remains to show is that this is a one-to-one function. One. Yeah, is one, and this will finish things off for us. So let's suppose that f of okay, so suppose that I have two cosets, say tau and tau zero or tau m prime and tau zero m prime, plug them into the function and assume that you get the same output. So this means that tau of u is equal to tau not u. And hence, of course, these are automorphisms. Remember, the tau and the tau naught come from L prime. So I have tau naught inverse tau u is equal to u. And of course, what this means is it's since tau naught inverse tau fixes u, and m is equal to LU, right? Because remember, this is what we did at first and reduced this case here. Then tau's inverse tau fixes all of n. And so, what does that mean? Well, if tau inverse, or if tau zero inverse times tau fixes all of n, then tau zero inverse tau is actually n prime. And of course, from group theory, we know that tau zero inverse tau in n prime means that the coset tau n prime is equal to the coset tau n prime. So F is 1, and so and that is what is desired. Okay, any questions? Okay, let me recall for you the next lemma here. And I will leave that to you. Prove, so. (8.2.11). Like K and F fields. And let's see, H and N. Yeah, that's good. H and N subgroups of the Galois group. If the index of H and N is finite, if this is finite, then just as 4. The proof is simple, so I encourage you all to see if you can kind of work through that. Okay, any questions? Okay, I've got one more that I don't really think requires proof, because basically this next lemma is kind of tying together some of the pieces that we had earlier. So lemma 8.2.12. And let K H is set in. So this is just same situation we had before in the previous two lemma. If L is closed, quick reminder, this means anything to be closed means it equals its double prime. In general, a group field, that doesn't matter, is contained in the double prime, is closed if it's equal. And the degree of M over L is finite then M is also closed. And similarly, if H is closed, and the index of H and N is finite, then N is closed. And H prime in prime, this degree is equal to the original index. And C, if F is finite dimensional in Galois. And Galois over K, then all intermediate fields and subgroups are closed. Intermediate fields and subgroups are closed. And the order of the Galois group of F over K is equal to the degree of the extension. And like I said, most of this is just a recap of what we have here, but see if you can fudge in the details. Okay, so at this point, with this lemma in hand, so we already showed last time that we had one-to-one correspondence between closed subfields, closed intermediate subfields, and closed intermediate subgroups. And so this kind of wraps it for the case where F is finite dimensional in Galois. Now there's one more statement that I have to deal with because it was that business about the normality, right? So F is Galois over every intermediate field, but the intermediate field is not necessarily Galois over the base field, and you need normality to get that. So we need to dig up just a little bit more to finish off that last statement of the fundamental theorem of Galois theory. So let me give you a definition here. Any questions so far? Okay, so far. Okay, so let me give a definition here. Eight point two point 13. Let sigma in the Galois group of F over K and fields. Probably should have said what that these fields first. So E is an intermediate field of the extension. We say that one. E is a stable intermediate extension. or sort of say E is stable, we say E is a stable intermediate extension if sigma E is contained in E for all sigma in Galois group. Now, let me before I go further, point out something, and that is, do not confuse this with some kind of fixed field thing. This does not mean that, sigma E equals E for every E and E. All this means is all the stuff in E goes into E, right? But it could be kind of moved around. Let me give you, actually, let me finish the definition. Let me give you an example of kind of contrast here. B or 2. If tau, there's a place there. I think that sounded funny. We say tau in the Galois group of E over K. So now tau is maybe not an automorphism of full field F, but it's an automorphism of the intermediate field E that fixes K. We say this is extendable to tau. Anybody want to guess what extendable means or how we want to define this?
F such that when we only have this part, then it acts as tau.
Good, yeah, that's exactly what you want it to be. So we say it's extendable if there exists a sigma in the Galois group of F over K. So there's actually this big automorphism of the entire field such that when you restrict sigma down to E, you get precisely tau. So in other words, tau can be grown up to this larger automorphism of F that sort of, when you restrict it down to E, gives you the original tau. I wanted to give you, let me sort of contrast this business about another example. Let me give you something to refer to here. There we go. Example 822. So for this example, it might help to refer to table from example 822. Remember where we looked at the Galois group of Q omega alpha over Q. In this case, I'm going to let F equal Q K is equal to Q. Now, the field this intermediate field is stable, right? Because any element of the Galois group of F over K, if you look back at that table, takes omega to omega or omega squared, which is also right? So if you apply any automorphism of that big field, Q adjoined with omega and alpha, if you apply it to this little intermediate field here, one of two things happens. Your automorphism takes omega to itself, in which case certainly you have this, and in fact, you also have that everything is left alone. The second case is the automorphism takes omega to omega squared, or to its complex conjugate, if you like. And again, you have this going on because this thing also contains omega bar, which is a square. Notice that one example of one of these automorphisms that moves this around but doesn't, it keeps it stable, but it doesn't fix every element, is in fact the automorphism that is complex conjugation, right? On the other hand, the field U alpha is not stable. As there exist automorphisms that take alpha to alpha omega and automorphisms that take alpha to alpha omega squared. And of course, if you go from, if your automorphism of the entire field takes alpha to alpha omega, this thing is real and alpha omega is not. So it has to move the field outside of itself. So it certainly doesn't satisfy this. Right? Remember, what it means to be stable is it may move the elements of the field around individually, but they all stay inside. Any questions? Okay, so how about a little lemma to go along with this? Let's suppose fields and let's A if is stable, then E prime remember, E prime is a set of automorphisms of F that fix E. So it's the same thing as the Galois group of F over E. And this must be normal in so if you have a stable extension, then the Galois group of F over E must be normal in the Galois group of F over K. And on the other hand, if H is normal, suppose you find a normal subgroup of the Galois group, then H prime, which of course now is a field, is a stable intermediate extension. Okay, any questions on that? So let's get to proving this. Proof. Let's do A first. We want to show that if E is stable, then E prime must be normal in the Galois group, that's over K. So let U be an E. Sigma in the Galois group of F over K. And tornado in Galois group of F. Now, what we need to do is, of course, our goal. We need to show that this thing is normal in this, right? So need to show that sigma sigma inverse is still in the Galois group of F over E. That is to say, we need to show that that conjugate automorphism has to fix or still fixes U. So right. Well, and what we've got is E is stable. E is stable. So for all sigma in the Galois group of F over K, sigma of E is contained in E. Right? That's what we got going for us. Well, check it out. If you have sigma, tornado, sigma inverse, U, sigma inverse, well, sigma is an element of the Galois group of F over K, so is sigma inverse. So this piece is actually in E. Agree? Because U is in E, and when you apply any automorphism, it's still in E. I don't know what it is, I just know it's in E. Right? And this is equal to sigma inverse U. Because this animal has to fix everything in E, right? Since this is in E, basically this thing leaves it alone. So you've got that. And of course, when you have sigma inverse sigma, you get therefore the Galois group of F over E is normal in of F over. Okay, and finally, for the next part, finish this up today probably. We want to show that if you have a normal subgroup of the Galois group, then its prime is a stable intermediate extension. So in this case, let's sigma be in the Galois group of F over K. And let's suppose that H is normal in and B in H prime. Now remember, that's the intermediate field. We need to show the sigma B is still in H prime as well. That's what we need for stability here. So in other words, we need to show that. For all. For all tornado in that H, that. That is, this is what it means to be in H prime, is that it's fixed by everything in H. And to this end, normality of H, sigma inverse is in H. And hence, right, so sigma inverse tornado sigma actually has to be B because B is in H prime, therefore. So. And so we have that this is stable. And that's it for today. Any questions on that? Any questions? Okay, well, you all cogitate this and we will see you on Friday.